I am Anna Petz. I am the chair of ARGA, and it's really awesome to be here today at the joint webinar with WOMEESA for December 2024. Before we get going, I'd just like to acknowledge we're all meeting on the traditional lands of First Nations people, and just like to acknowledge their continuing custodianship of the land, and pay our respects to elders past, present, and emerging. And I think we have a couple of announcements. So we do have this webinar series will continue into 2025. We will have in February, we will have our meeting with sorry, I should say this, Roland Gotthard on the geology and economic potential of evaporative allanite, which would be really exciting. So we'll get a reminder out to get those in the diary and register for that. And we will have more meetings into the new year, which is really exciting. So this is our last webinar for the year, and just make sure you check out the ARGA YouTube, which can probably we'll chuck in the chat sometime, because that way you can go and have a look at our past talks as well as last month's, which I still need to upload, but that will be there soon. And if anyone is interested in presenting on our ARGA webinars, please do shout out. We're happy to have a 15-minute presentation. We're happy to have a 1-hour presentation, everything in between. So today I'd really like to welcome Dr. Gresley Wakelin-King, who's here today to talk about dryland rivers. And I think she'll introduce herself much better than I can. So I'm going to hop on mute and pass it over to Gresley. So welcome, Gresley. Thank you so much for joining us today.
Cool. Thank you. Thank you very much for inviting me. I'm going to share my screen. Go share. Okay. Is it nicely working? Is it sharing? It's all good?
Yep.
Excellent. Okay. And my instructions bar is hopping around up and down in a really exciting way. Okay. I don't care. I'm ready to go. All right, I'd like to start by acknowledging the Wurundjeri people on whose land I live and work on, and also the First Nations people across the Australian drylands, and acknowledge their elders past, present and emerging. Oh, come on, PowerPoint, do thing. Yes, okay. So I want to talk to you today about the relationship between rivers and regolith and the work that I do, and some things that I'm interested in research of the landscape evolution of the Australia's drylands. And I'll start by saying I'm a geomorphologist with a geological background. I'm a consultant, and a lot of the work I do is trying to bring geomorphology information into land management. So typically my clients want to know things about how their landscapes work that assists them in making better land management decisions. This is my current area. This is the Karriapundi swamp in the Bulloo Lowlands, on the border between Queensland and New South Wales. And I'm going to sneak up on this as a topic of conversation in a little while. In overview, this talk has got 3 threads. One is stream capture. One is the stratigraphic succession in some of these interior lowland basins. And along the way, intermittently, I'm going to be touching base with how these things affect drylands ecosystems, because this is the information point for my clients. The regolith gang that we're going to be talking about today is silcrete and gibber plains, the underlying soft leached weathering profile, vertic soils and sands in fluvial transport. Okay, some of the best places in the universe. The interior lowlands includes the Carpentaria basins to the north, which I've never worked in, so they're not on this map, and the places that I'm interested in, which is the Lake Eyre Basin, the Murray-Darling Basin, and their baby brother squeezed in between the two of them, excuse me, the Bulloo Basin. This is what it looks like on the Google Earth. I've put the outline of the Lake Eyre Basin there. The first thing to know about this area is that the landforms and the landscape evolution and the rivers and their drainages are all affected by some substantial tectonic, I guess they're tectonic context. So if we just have a look, for example, at aligned valleys, there are some really large scale structures of valleys which line up, and I've just coarsely plotted some lineaments on there, but there's lots of them in there. As well as the valleys, there's a series of swamps, and they also fall along a trend line. So these swamps are all like local epicenters, right? They're local areas of subsidence. They're not getting a lot of sediment input, so they're vacant space waiting for water to get into, so they're nice and slushy when it's wet. So basically what's going on here is that there's an enormous crustal sag, which is basically the whole of the interior lowlands. Not sure if I should say crustal sag, maybe it's a mantle sag. This is all outside my area of expertise, but it's a huge sag over this part of Australia. And then kind of superimposed on that are these wrinkly bits, I tend to think of them as. So doming and subsidence that forms these valleys and hills. Now, the other thing that's really interesting about this area is the regolith context. So Australia is unusual on a global scale for the amount of vertic soils that we have. And I'll come back to what exactly a vertic soil is and why we care later. But just know for the moment that there's a massive bunch of it here. And it's one of the things that makes Australian drylands different from some of the overseas drylands. And this belt up here is more or less in situ. So these are the vertic soils developing on their parent material, which is mostly the top levels of the Eromanga Basin. And then a lot of this stuff down here is transported vertic soils deposited in the river valleys. So if I go back up to the valley alignments, you can see that the vertic soils are deposited, are mapped within these valleys. The other regolith thing that's pretty cool about this landscape was is the Paleocene-Eocene Glendower Formation or Air Formation, depending which state you're in, and its associated silcretes. So these are present in a lot of places, and there was a very cool little a post on the ARGA Facebook group just a couple of days ago showing one of these tabletop hills in real life. The geological mapping of their outcrop is these white polygons, but the mapped outcrop doesn't really do justice to how extensive they are. So the translucent white polygon is a very quick and dirty plot of a kind of a huge belt of hard silica-rich country that goes across this area. So one of the reasons why regolith character is important to the work I do and for my clients is that regolith character mediates the runoff response. So when rain falls, how much of that rain gets into the fluvial system? This is much more important in the drylands than it is in the perennial coastal bits, because typically in perennial landscapes, you've got more reliable blanket of soil and also vegetation. Whereas here in the drylands, we've got a much more immediate response to the runoff when rain falls on it. So we've got some real extremes here. The silcretes and their underlying leached bits, these are like the tin roof of drylands country. Rain falls on here and it goes off it really, really quickly. It's like 100% runoff in many places. The opposite extreme is these vertic clays So this is in the floodplain of the Thomson River in Queensland. It's part of the Cooper catchment. And many of you may know vertic clay soils or vertisols, also known as cracking clay soils or black soil country. And as you can see here, it develops like cracking at multiple scales. And this stuff is like a ginormous sponge. You can have absolutely zero runoff from water either falling on this stuff or flowing over this stuff. It takes a really long time to get saturated to the point where it will allow runoff. So big extremes there. And these extremes between the runoff response between the different kinds of regolith, these are one of the things that drive the variability in drylands rivers. So the highly variable flow regime of drylands rivers is one of the things that makes those qualitatively different from the things that we think of as being normal rivers, temperate zone perennial rivers. Okay, so regolith character really important for understanding the rivers, and this is one of the ways that it's really important. The runoff determines the amount of water that comes into fluvial transport. Understandably, that means how much water is there in the river. The amount of water in the river translate to stream power. That means how much energy is available for the stream to do its work in landform creation and maintenance. So the runoff is directly linked to what kind of habitat we've got in these dryland systems. Okay, here is the Neils catchment. This is on the western side of Lake Eyre. It's a stark, but I think very beautiful landscape. And it's jump up country in a big way. So the general situation is silcrete or gibber as a protective cap over leached profiles. So the way this expresses in the landscape is broad, low relief gibber uplands and low elevation but high relief valleys. So the valleys they're kind of flat, you know, in the middle bits, but they're high relief at the valley margins. And the valley margins often show fragmented soft mud rock. And this is what it looks like in terms of their drainage networks. In the silcrete and gibber plain uplands, you get these broad and low gradient dendritic drainage networks. So really, really flat, as you've seen in the previous slide, but very, very broad. Whereas the high relief valleys, they've got valley aligned drainage or, you know, slope aligned drainage and very steep in places. So these valley margins are quite steep, like you couldn't take a car up most of this. Now, what that means in terms of the sediment load that the river systems carry, if we look at the gibber uplands, you've got potentially high runoff if there's a big rain event, because these are, you know, high runoff, tin roof type regolith, but it's a super low gradient and the sediment that's lying around waiting to be collected is big lumpy bits of gibber, quite coarse sediments. So basically there might be some heavy rain here from time to time, but there's not very much sediment that gets entrained, and consequently these rivers often have little to no bed load. In contrast, the valleys have got places which are not only steep, but they've also got gravity-assisted sediment entrainment and they're high runoff. So when it rains really hard in these areas, you get a lot of sediment put into the fluvial system. And so the rivers have got coarse and abundant bed load. And this translates into some markedly different habitats. So here's some of the rivers. Here's one of the creeks that comes off the Gibber uplands. This is Hookie's Waterhole near Udnadetta. So in these Gibber uplands, if you get a mega flood scour event like some 1 in 300 year flow event that's big enough to carve some scour holes into the floodplain. There's no bed load coming down with this, and so the carved hole remains an empty hole in the floodplain, and it fills up with water and it makes a water hole, and so your biota is happy. Yay, happy fish, happy trees and lizards. Whereas in the other place, the valleys, you might have the same kind of mega flood scour event that might carve out a hole in the floodplain, but that hole immediately fills with a whole lot of coarse sediment. So, you know, it's a perfectly nice place to throw your swag down, but it's not a water hole. Okay, so now we're going to have a look at what these two different fluvial styles mean for the pace of erosion. We've come back to this Google Earth picture of this bit of country that's called the Jump Up. And we've got the Neils River here and ARGA Creek, which is a tributary of the Neils. And the upper Neils River is these uplands, silcrete and gibber plains and dendritic drainage, and it weathers by really slow downwearing. So it's broad, but like I said, not much sediment entrainment, so there's not a lot happening. Whereas the high relief valleys, they develop by rapid scarp retreat. So you can see the sediment being pulled down the sides of these valley margins, and as soon as it undercuts this silcrete cap enough to make it collapse, then, you know, it all comes down here. So clearly what we've got here is rapid scarp retreat. What we've created is the scarp retreat is cutting back into the topographically higher drainage network. Okay, this is what it looks like from the ground. This is the high plain that is carrying the dendritic drainage, and this is the lower valley in ARGA Creek. This is the topographic elevation profile, and that X is where I'm standing to take this photo. So I want to emphasize that both this creek area and the ones on top of this flat country, these are both at about the same level of stream order in the drainage network, right? They're kind of equivalents. They are very dissimilar twins, if you like. So what we've created here is ideal conditions for stream capture. The topographically lower drainage encroaches on the uplands drainage, and it provides a gradient advantage to either one or both segments of the captured stream. So basically the upper drainage has been offered a much more efficient way to get down to base level if it jumps into the lower drainage. So let's have a look at some examples of this. This is a Google Earth image, a close-up of a place not very far from the Jump Up, those last few photographs that I've shown you. And the upper drainage in the dendritic in the Gibber Plains is these white arrows, and the scarp drainage down into the lower valley is the black arrows. And you can see that the upper drainage level is draining towards the north and north-northeast, whereas the lower drainage level is draining towards the east. If we zoom in much closer, we can see that actually this arm of the upper drainage has been captured by this bit of stream encroaching its scarp back into the flow path, the channel line. So this channel now takes an absolute right angle turn and goes down into the lower valley. So this bit of scarp here, this bit of creek here has been captured by the lower drainage line. So one of the kind of coolest things to look at is the way your drainage becomes really disorganized and disarranged when you get stream capture happening. This is a digital elevation model of the Neils and Peak catchment, and it shows the the big reverse S shape in the drainage near Oodnadatta. And I'm reasonably sure that this is also another bit of captured drainage. So the catchment in the yellow, which is not shown on this map, this is the Macumba River. And these bits of creek, you know, they're heading fairly off into the east up until they take this amazing right angle bend down here and cut down through the scarp, and then another right angled bend to go along down into the Neils. I think there's probably some other things as well as drainage caption here. So I think the advantage of the Neils has been also increased by probably some doming here in the Macumba. But anyway, here is a place where this bit of drainage used to go one way, and now it goes down and it joins the peak. And when I started seeing this, I started seeing this kind of stuff all over the place in the Lake Eyre Basin. So this pretty little thing is the top of the Diamantina catchment. Here on our regional map, we're looking at the northern edge of the Lake Eyre Basin. And beyond the edge of the Lake Eyre Basin here is where the Carpentaria Creek rivers are trying to cut back towards the south. So it's like a head-to-head battle between the two catchments, I reckon. They're fighting it out. And in this particular instance, I think the Diamantina has won over the Carpentaria coast, because this creek used to be going off to the north-northeast, and it's coming around in a big circle, and now it's heading down towards Lake Eyre. And I think this is happening at even larger scales. This is the Bulloo catchment, a digital elevation model. So on our regional map, we are here. And you can see that the catchment takes a bit of a dogleg here. Now this upper part of the Bulloo catchment goes pretty much to the south. And if you look at that blue tint in the DEM, you'll see that there's a lower elevation bit that continues down into this bit. This is the Peru catchment. So I think it's quite likely that the Bulloo basin only used to go up to here, and then it's done a big capture on this bit of the upper Peru. And yeah, now it's a bigger, stronger river, and the Peru is a sad little stub of its former self. So the things that happen as a result of stream capture, as well as the cool things that happen to the drainage geometry, you get gain or loss of a catchment area. So this is what the upper bit of the Neils River used to be until it captured this bit of the Macumba, and now it's got access to all that amount of catchment. That changes the flow sizes and the river energy, as previously discussed, and also raises the opportunity for changes to the amount or the types of sediments that can flow into the catchment, the river that's done the piracy. There's also some really interesting stuff about how it changes the pace of landscape evolution and makes some really substantial changes into kind of, I guess, the transitions of change of landscapes. I'd commend these couple of papers, which make some really interesting reading, and the citations are in the chat. Okay, I'm going to completely abandon stream capture for a minute, and we're going to go to the Cainozoic sedimentary record in the Lake Eyre Basin, and particularly its application to the ecosystems that exist there now. Where the next few photographs and slides are going to be mostly the Cooper catchment and the Diamantina catchment. And the Google Earth image, here's the Diamantina is coming down through here. And this is a jolly big swamp called Gorda Lagoon. Gorda Lagoon is amazing, right? It's just this huge, super muddy, super boggy hole. it's a lignum swamp. This is the main flow path, right? This tiny little muddy channel. This dude here is more than 2 meters tall. So this lignum is like 2.5, 3.5 meters tall and so dense that you can't force your way into it, even, just as a single person. The biological density here is just huge. In contrast, here is one of the creeks in the Cooper system. This is one of the longer main water holes, and it makes this beautiful river with a steep bank and gum trees and fish and everything. Really pretty. But generally speaking, in the Lake Eyre Basin, what we're looking at is elongate valleys of tectonic origin. The valleys are hundreds of kilometres of flow paths and channels. And these swampy areas, these black in the Google Earth image, hundreds of square kilometres of dryland swamps, really, really important to local ecosystems and various endangered species and the migration paths of water birds and all sorts of things. Looking at the stratigraphic record in these elongate valleys, it's surprising, but there's actually several hundred metres depth of Cainozoic section in some of these places. So the Queensland Geological Survey, for example, has mapped, I think, 200 or 300 metres thick in the valley of the Cooper Syncline, which is where Cooper Creek flows now. So stratigraphically, what we're looking at is a Holocene mud layer, which at Cooper Creek is about 30 metres thick, and it is conformable over the Pleistocene, the Cataperi Formation, which is quartz-rich sands, variously tens of metres thick. And I just want to credit not only the image, but the research of this, Jerry Maroulis, who was at that time working in the Wollongong University Quaternary Research Team. So he's got some really interesting papers where he's mapped out the stratigraphy. Okay, so Holocene, Pleistocene sands, bunch of other units which we don't care about. And then the other thing at the base of the Cainozoic section is the Paleocene, Eocene air formation and its correlative in Queensland, the Glendower Formation. And they're really strongly associated with various silcrete Juricust profiles. And then below that is Mesozoic. We don't care about that either. Okay, let's have a look at what this stratigraphy looks like in terms of the ecosystems. So here's the vertic floodplain muds, cracking clays. They've got a really strong shrink swell behaviour. They're self-mulching, which means if you let them dry out, they'll break into a bunch of crumbly little bits. These crumbly little bits, these mud aggregates, they behave like sand in fluvial transport. This is a really important point. They behave like sands. They are robust. They are muds, but they're robust in fluvial transport. They can be transported really long distances and deposited under fairly high energy conditions. Their character influences the channel country fluvial style. So some things that are quite important to the ecosystems, like the steep banks of the waterholes and the gentle floors of the waterholes, for example. They absorb water, as previously said, and when they form a thick mud layer, they can be a really tight seal. And we'll see why that's important in a little bit. They're biologically productive, but in a pretty specialised habitat, particularly the swamps are a really specialised habitat. And here's some pictures of the classic channel country fluvial style with discontinuous channels set within a broader floodplain level flow path. And these darker bits are kind of swampy and kind of muddy and probably full of lignum, and don't get bogged there. Okay, the next thing down in our stratigraphic succession are these Pleistocene sands of the Cataperi Formation. So they were deposited during a past wetter climate. Here's a picture of the sands, image credit Jerry Marillis again. When these sands were laid down, this was an active meandering river, a high energy system, lots of water, lots of channels and scroll plains. Now the Catapiri mostly exists in the subsurface beneath those floodplain muds. And it is important that it hosts the unconfined aquifer. So these sands are very permeable, and obviously the aquifer is of interest. Sometimes these channels are excavated and remobilised into near channel landforms, like this source bordering dune along the sides of the Andrewilla waterhole in Goyder's Lagoon. So here is a really cool thing. Next time you want to do a Google Earth field trip, I highly commend this. If the mud layer that overlies these Pleistocene sands is like a little bit thin, the aquifer is actually visible through the Holocene floodplain muds, or the sometimes a thin layer of fluvial sands, if there's any. Like the channels and the scroll plains of the Pleistocene rivers are visible on Google Earth. Here's an example from the Simpson Desert, just north of the Goyder Lagoon. And these pale shapes here that you see, these are the swoopy shapes of the channel loops of this Pleistocene meandering river. They're not at all related to the present day drainage. In fact, this is sand dunes, the orange sand dunes. You can see them trending this way. So these underlying loops are cross-cut by the overlying landforms. And you can tell that they carry water because they show up on the water observations from space, which is on the Geoscience Australia, Digital Earth Australia data hub. So this is so cool. You can see these things. Once you get your eye in, you can start to see them in a lot of places. Now, in terms of the ecosystems, this unconfined aquifer is really important because when it's sufficiently shallow, it can either support or suppress the surface vegetation, depending on certain local conditions. So here's an example, also in the Goyder Lagoon. This is a Google Earth picture of the modern dune, the orange thing, and you can see that it overlies and cross-cuts this big, thick, pale thing, which is the buried paleochannel, and these are parallel, slightly curvy stripes. That's a buried scroll plane. I'm standing right here on the crest of this sand dune, and I'm taking a photo along the boundary, the edge of that paleochannel. And check out what it's doing here to the vegetation. There's basically enough water available to the roots of plants on one side to support vegetation, and absolutely not on the other side. This is really interesting stuff, but you know, this is important in a lot of places. So the near surface unconfined aquifer, that is the Catapiri Formation. I've identified, I or other people who've also looked at these things, including lots of fabulous work from the South Australian Geological Survey, have identified this stuff like all through here, all the way down the Simpson Desert and the Strzelecki Desert, up here, down here. It's cool. It's everywhere. Love it to bits. Okay. This brings us back to my clients and the work that I'm doing and drylands ecosystems in the Karriapundi swamp. Because my clients in New South Wales based, I'm only allowed to care about this bit of the Karriapundi swamp. I can see that there's dark swamps up here. It's in Queensland. I don't care about Queensland. I mean, I do, but I can't put it in my report. So my concern here is what's happening here in this bit of the Karriapundi swamp. What landscape processes are supporting the ecosystem values of this Ramsar listed wetland? And unlike so many of the other swamps that I've dealt with, this doesn't look like it's one of those nice, rich, muddy, lignum-rich areas. In fact, um, you know, it doesn't look to me like it's one of these wet places with lots of vegetation. In fact, it reminds me much more strongly of gypsum ground like you might find in a player lake system. So when I went out to do field work here, I was kind of expecting that I would find some kind of player lake or evaporite system or something, not wildly supportive of rich ecosystems. And actually, I found a whole different situation. What I've got exposed all across the area is a whole lot of clean, pale sand. And the vegetation is quite sparse in most places, but it's still vegetation that likes a little bit of water. So things like cane grass, a few bits of lignum, a few bits of samphire, but not a lot of it. So quite contrary to my expectations here. And obviously, I'm wondering why. I had a look around, and the Caterpillar equivalent sands are here. So here's an example not far over the border in Queensland with a nice little paleochannel enclosing a series of bars of the scroll plain. But I'm not seeing a lot of the vertic mud here. Why is that? My hypothesis is that the Bankania Basin may have had less access to the mud aggregate sediments, which have obviously formed such a big part of the floodplain muds elsewhere in the interior lowlands. And that's led me to further to wonder whether in the Lake Eyre Basin, if the sand to mud facies change may also relate to something to do with sediment supply, as well as obviously Cainozoic climate cycles. Now, it's possible also that this change to supply may take place by catchment scale stream capture. So let's have a look at the footprint of the Cooper and the Bulloo catchments over the in situ parts of the vertic soil. Here we are back at our Google Earth again. Here is the outline of the Lake Eyre Basin, and mostly what we're looking at here is the upper part of the Cooper catchment, and this wee little bit down here is the Bulloo Bankania Basin. Looking at the drainage, we can see that indeed the Cooper has got an enormous footprint in this vertic soil source area, whereas the Bulloo has only got access to a really, really, really tiny little bit. And furthermore, we can see that this belt of hard silcrete country occurs across the drainage lines and is kind of mid-drainage in the Cooper, but is kind of right at the top end of the drainage in the Bulloo. Also, what I know is that I've been to Junda, and at Junda there's a great big there's a choke. Like, it's a really, compared with the rest of the Cooper system, the Junda is a narrow valley with an energetic down-cutting river, immature landforms, and really immature valley margin sediments. So this is a clip from a report that I wrote about this area. You can see that the scarp is cutting back into old land surface, and that oval there, this is a percent for scale. And look at these, really thick bouldery bits at the margin here. This is a real high energy part of an otherwise low energy system. So it seems to me a very possible mechanism that drainage extension through the silcrete could be a point at time in which the Cooper catchment got access to a whole heap of vertic soils, mud aggregate particles to enter into fluvial transport, and this could have facilitated the sand to mud facies change in the interior lowlands. So my conclusions are regolith is an important influence on habitat, so in land management we should know about it. The regional aquifers sand to mud layering influences the local ecosystem, because I think that the mud is acting as a seal and a cap to protect that regional aquifer and the underlying sands. And that finally, drainage capture is a significant driver of landscape evolution in these areas, and it's a possible mechanism for the interior lowlands sedimentary record. Okay, and that's all I have to say.